My name is Deborah Fowler. I'm going to discuss a technique that I use in my procedural animation class, which I call the two-point constraint problem. What we have right now is a rod that is moving according to an add node on a tube, and it looks like the rods are together constrained, but we're actually using equations to calculate this. So how do we do that? First of all, we calculate the distance between the 2 points, because at any given point in time, we know that yellow rod, even though the length is changing. I'm going to call that rod D. And the other 2 rods are rigid, so they're a set length. Little r is the green rod, and big R is the purple rod. What we want to find are the desired angles that you see in red. So how much do we need to rotate those rods in order to make them look like they're connected? So let's get started. First of all, we're going to use the dot product, Pythagorean's theorem, and vectors to define our equations. To start with the dot product, we're going to find the dot between D, our vector, and the x-axis, the reference axis, to find angle S and angle T. Then we're going to find the angles in the triangle, angle G and angle E, using Pythagorean's theorem. But Pythagorean's theorem applies to right-angled triangles. We're going to see how that applies. What we're going to do is we're going to take our 2 angles and subtract them to get our desired angle. So if we take our orange section and subtract it from the blue, we end up with our red desired angles and an expression based on those 2 angles. The Pythagorean theorem applies to right-angled triangles. So we're going to drop down a perpendicular, which is going to give us 2 right-angled triangles, the green one and the purple one. What I've done is chopped the vector D into 2 parts. So we have big D minus little d and little d. We know that the squares of both sides equals the hypotenuse squared, so we create an expression. I'm calling the side that is shared red. So red squared plus the little section d minus d squared is equal to r squared for the green triangle. Similarly, red squared plus little d squared equals the hypotenuse of the purple triangle. So we have 2 expressions. What we're going to do is reduce these and simplify and solve for little d. So on the top expression, I'm going to subtract that value d minus little d to move it to the right from both sides. Then I'm going to do a similar thing on the bottom equation, subtracting d squared from both sides. What we have now are 2 equations that our common side are equal to, so we can equate those. We now have an expression that I'm going to expand out the polynomial and then extend the minus sign through the parentheses, get rid of those parentheses. Then we can see we have d squared on both sides. If we add d squared, we can get rid of those. Now I'm going to try and isolate little d. So first thing, I'm going to subtract r2 from both sides, as well as adding d squared. And finally, dividing by 2 large d. This gives us an equation for d. So d is in terms of known values, the length of the rods, and big D. Big D can be calculated based on the locations. So let's save that formula for later. Okay, so let's take a look at that vector D. D is defined by the points. We also know that the length of a vector is equal to the square root of the square of its sides. And if we want to normalize a vector, we divide by its length. So looking at our vector D, we can see it's defined by our 2 points. And we have definitions for our 2 sides. This gives us information that we need to calculate D. So let's also save those for later. Now, the next step that we want to do is look at the cosine. So we have two right-angled triangles. What we can do is find angle G and angle E by using the properties of cosine. So the cosine of angle G on the green triangle is big D minus little d over the hypotenuse r. The cosine of the purple triangle of angle E is little d over big R. If we take the inverse cosine, we can then get values for each of those angles. Let's also keep those. So next, we want to look at the dot product. So we're going to take the dot product of the x-axis reference with the vector d to give us angle S and angle T. The dot product is defined as the normalized vectors times the cosine of the angle between them. It's also defined by an equation that uses its coordinates. So if we use this with our particular situation, we have the x-axis dot with our vector d. That becomes the following. And you can see that using this equation, we end up with x1 minus x0. If we take that and equate that to our normalized vectors times the cosine of the angle, we end up with x1 minus x0 divided by the length of d equals the cosine of the angle between them. We already know what the length of d is in our formulas up above. Expanding that out, we end up with angle t equal to the expression that you see here. So now let's keep that. I'm just going to quickly flip the value so that angle t is at the front of the equation. And next, we want to find angle S. Well, because we have parallel lines, angle S is just the complement of angle t. So in other words, 180 degrees minus angle t. If you expand this line, you can see that the parallel line, really what we have is that arc subtracted from 180. Okay, so next, what we have is a value for angle S. So we're going to keep that formula as well. So what we've done is we've come up with formulas that we can now use in a point wrangle. And that will give us the motion that makes them look like they're connected. So using a details point wrangle node, just take a look at that. So let's take a look at what that looks like in the wrangle node. You can see here that we have our values for big R and little r, which are just the lengths of our rods. We're retrieving a value of x1, y1. We're grabbing a point, which is the point that's being rotated around that tube. We have x0, y0, which we're taking from that. The value of d is just the square root of these values squared. We then take little d and define here by r squared minus little r squared plus d squared divided by 2d. Be careful with the parentheses. Angle E is the arc cos of little d over r. Notice that we're converting to degrees because point wrangles use radians, but we need degrees for our parameters in our values. Angle T is, again, this expression here. We're just using d since that is already defined here. And then we define a rotation angle for the purple rod and the green rod based on our calculations. The reason we're going in negative direction for the green rod is because we are going away from the x-axis and the angles are defined as positive going this way. So that gives us the values in order to make these look like they are constrained. I should also mention that the point wrangle is in details only mode, so you only have to calculate this once. So there's no wasted calculations. I'll just, you can see here that this is details only once, and there's our network. So we have our green rod. We're retrieving our values here by using a details expression, which is just referencing the point wrangle node for that particular rotation. Same thing over in this node. And here's our point wrangle node, which is attached to our wheel that is spinning. And that's it. So I hope you've enjoyed this. There are sample files on my website, and thank you for watching.